is recorded.
So, get going for today. For those who, if you haven't noticed, the exam scores have been posted on Canvas. I have the graded exams here with me in class that you can pick up at the end of class. So I posted scores and back exams, and I'll post the solutions. Average went up from last exam. And it was a point where I was, yeah, I didn't feel a need to try to do exam redos because everyone failed the exam or something. So yeah, overall the exam average went up significantly from the first exam, so that's good. That's typically what happens. I mean, how much it goes up, I don't know. It depends on the semester, but typically the average goes up after the first exam. So yeah. But so I'll hand that back. I think all of the scores are updated on Canvas. Like I said, I'll post solutions. I was waiting to post the solutions, but I'll post those solutions online sometime today. Okay. For the questions. But yeah, any questions?
Question 3 on the quiz. The answer that it wanted was in Celsius. But it didn't tell us that. Because it's in Kelvin.
Oh, did I forget to say that?
Yeah.
Okay. All right.
Kelvin,
Let me note. Where am I making a note? So question number 3, right? All right, so I will go through that then, question number 3 on the online quiz, and give people credit for those who answered the question correctly using Kelvin instead of Celsius. I usually try to remember to say units, but obviously I didn't. So, but yeah, so I'll do that. Any other? Yep.
Well, regarding that, since KB was given in Kelvin, if it stated to answer in Celsius, how would we convert KB to
So you don't need to. You wouldn't need to convert KB. So the problem in question is a colligative property problem of a change in freezing or boiling temperature. I forget. Right. Yeah. And so you calculate the change in temperature, which let's say is minus 5 degrees Celsius. Well, that change in temperature is the same change in Kelvin, right? Minus 5 degrees Kelvin and such, right? So yeah. Any other questions? Yeah, like I said, the exam You know, on average, obviously I don't speak to anyone's personal experience, but on average, the exam went better than the last one. Even though I also felt that it was a little bit longer than the last one too. So, you know, and I don't feel that I was necessarily more generous with my grading. So, you know, that I feel it's a reflection on people gaining a better understanding of the material, performing better. So, right. But yeah, that I'll post the solutions. Anyone has any particular questions, I can kind of discuss any of the, otherwise.
Out of curiosity, which question was the one that you really wanted on the exam? Was that four?
Yeah, question 4, I liked. I don't know, I just thought it was fun. Probably most people didn't find it fun doing question number 4. But I guess I liked it because I felt like, at least mathematically, it wasn't challenging. It was long mathematically, which was my issue with it. But you know, you had to think about what was happening in the problem, but you know, yeah. So in question 4, right, you have and this was a common thing that was overlooked by a number of people, but right. Let's go to this, right? Most people said, okay, the heat transfer from the ice is the same as that from the water, right? And they did the water fine, but then the ice, you heat up the ice, you then melt the ice, and then you heat up the liquid that's formed from melting that ice to a liquid, right? And that gives you the total heat given off by the ice, which is a constant, and then your T final appears here. And so the final temperature was 279 Kelvin. A lot of people just use this here, or I think this here, and left T final for whatever it is for ice. And I think you get a temperature that is maybe even higher than the original temperature, or similar to the original temperature. Maybe it's close to 293, maybe it's like 292 or something like that. But yeah, so you get something. When I originally made the problem, this temperature came out to be like less than the freezing temperature of ice, so I had to change some numbers around to make it so at least was above freezing temperature, right? And then after that, right, a number of people kind of, you know, said, okay, the heat transfer in the surroundings is 0 because you're just transferring heat between the ice and the liquid, right? And then they broke up kind of the heat transfer in ice and water, and for the most part, kind of did this stuff, right, where the water is just this NCP delta T, and then the ice again has the 3 phases. A lot of people kind of broke that up in those 3 phases. So, you know, a significant number of people kind of approached most of the question in the right way, but most people actually, that first part with getting the change in temperature, didn't do that. But that's kind of why I gave the problems, because it had that trick to it. I liked it, but again, most people probably didn't like that problem. So, other questions on the test? All right. All right. So as a reminder for the rest of the PowerPoint is virtual background. That's new. What is this all about? I'm curious. Sorry. There's a new option here. I'm wondering if I can be on my PowerPoint if I put the camera towards me. So out of curiosity's sake, we're going to take 2 seconds here, see what happens. Okay, so there's PowerPoint. That's supposedly as a virtual background. So if I have my camera, oh yeah, look at that. I can appear really horribly. This is awful camera. Yeah, I mean, I can flip it, you know what I mean? Okay, no, it's a lot better. Hey, look, it's me. I'm on my PowerPoint. That's fun. I wonder if I can I'm curious. Oh, can I move? I can move myself around too. It's exciting. Oh, I forgot, I need to change the, it's like the chat is like, yeah, it was set up on exam mode where you can only message me. Now people can message everybody in the chat or anyone privately if they want to. It's kind of cool though. Let's see here. I want to like, can I blow up the screen more?
Exit the chat, like close out the chat.
Yeah, but I want to go like full
No, how do you
screen.
go to, you need to, it's like your background or, the video settings?
Yeah. Yeah, it's fine. I mean, this is like a new like screen share thing, and so I don't know. Yeah, the problem is then it doesn't have the animation, so the solutions on these are already here. It's no fun. But that's kind of cool. Me here. Right, move myself around. I am part of the equilibrium. All right. Well, sorry, I shouldn't play with that. It's interesting, cool, but we'll just go back to. Oh, I don't know. People on Zoom do they like seeing me here randomly on the slide? Is that fun for you? I mean, besides entertainment value, is it actually useful? I don't know. Problem is like, even if I put myself here, right, I try to point at something, right, I can point in this like little box and then that's it. But so I don't know. Oh yeah, I can. I just entire screen down, and then you can't see anything else but my ugly mug. All right, I'm gonna go back to kind of normal stuff here. So sorry, played around with it. Maybe I'll try to design some things or whatever. Now that I never seen that option before, so it's something new. Anyways, sorry about that. Right. So what I was going to just say was that right, this week we're going to talk about some colligative property, or not colligative property, sorry, activities and two component phase diagrams, chemical equilibrium, which I posted all those videos last night. Got them up kind of late last night, so I apologize about that for anyone who's potentially interested in looking over those over the weekend. And I did post the lecture slides, but I think it was also late last night. So I was a little behind on that because of doing some grading and stuff. But yeah. And then the following week after that, we will basically be doing electrochemistry for the entire week. And then the week after that, which is the week before Thanksgiving, we will be doing probably statistical thermodynamics and talking about that type of stuff for that week. And then the week of Thanksgiving, we'll do a review. And then the week after Thanksgiving, we'll do a test and another review. And the week after that, we got the final, right? So that's, right, we're kind of on the home stretch here, right, for the semester. Okay. So that's kind of the rough outline of what we're covering when we're covering it. Okay. Any questions about that? All right. So got a question here. I have 0.05 moles of aluminum chloride I dissolve in 1 kilogram of water. Question is, what is the molality of aluminum chloride? What is the molality of aluminum ions? And what is the molality of chloride ions? So what would the molality of aluminum chloride be? 0.05, right? Aluminum ions, 0.5, and then chloride ions. Yeah, 0.15, right? Exactly, right? Things break apart, right? So yeah, 0.05, 0.05, and then 0.15 for those. Okay. Right. Right. And then if I had, say, kb of water, 6.2 kilograms per mole, what is the change in the boiling point for this solution? how would I calculate it?
KB times B.
Yeah, KB times B, the molality, and what molality am I using? The total 0.2, yep. Yeah, aluminum plus the chloride, right? So 0.05 plus 0.15, giving you 0.2, right? So that gives you roughly 1.24 Kelvin is the change in boiling temperature, right? Questions? All right, so now let's talk about activities of ionic solutions, okay? Related with those example problems, right? So in ionic solutions, surprise, surprise, the ions do in fact interact with each other, right? I got cations, I got anions, right? I got coulombic charges floating around in these solutions, right? For some reason I wanted to say like cats and dogs getting along, chaos everywhere, right? Roughly something like that. But anyways, right? And so often for ions in solution, the actual concentration of those ions is not related to kind of what we typically use, right? What you use in general chemistry and things like that, right, are typically the ideal concentrations, the ideal situations, right? While in real solutions, we want to consider the activity, right, the actual concentration, right, the effective concentration, not the idealized concentration of ions in solution, right? And so if I wanted to use, say, calculate, right, for this weak acid equilibrium, if I wanted to calculate what the Ka was, now we wouldn't actually include H2O here, right? Concentration H2O and activity H2O wouldn't necessarily be included, right? But if I wanted to calculate that, right, I'd want to use the activities of these ions and such instead of just the concentration, right? And so the question is, what are the activities of different ions in solution, okay? And so to get that, right, we again use the fact that we have our chemical potential, right, is related with the activity of the ion, right, which is related with some activity coefficient times the ideal concentration, right, the molality, right, that B sub B, right? Probably should have picked a different thing for the solute besides capital B here, right? But the molality of your solute, right, is sort of, you know, in its ideal thing, assuming it completely breaks apart, is what that B sub B is, right? So in the first example we talked about, right, the molality of chloride would be 0.15, right? B would be 0.15, right? The activity would be that 0.15 times whatever the activity coefficient is for chloride to get me the activity, right? And so that is what we're going to be kind of talking about and going over today is what are these activity coefficients for ions in solution, right? So that we can get the effective concentration and not the idealized concentration that we typically use. Okay. Right, and again, for ions, this is more important than other things that are mixed together and dissolved, right? Because again, you have these coulombic charges, right, and that's going to affect how well things are mixing together, right, and how much things are mixing in solution, right? Because if you think about having a solution with a bunch of ions already dissolved in it, right? So I got a bunch of salt in my water, right? I got a bunch of sodium ions, a bunch of chloride ions floating around in this water, okay, right? And right, each one of those ions, if they want to be dissolved in solution, have to be surrounded by some water molecules and can't be like right next to another sodium, right? Because you got positive ions repelling each other, negative ions repelling each other, right? So you need some amount of kind of space in the solution for your ion to be able to be dissolved in that solution, okay? And so if I try to keep on adding more and more sodium chloride, I'm going to reach a point where my solution just doesn't really have, say, the space to hold these ions, right, in the solution because there's not enough water molecules to solvate it, right, and keep it separated from other cations and other anions and things like that, right, so that in the end you'll reach a point, right, where you just can't keep on dissolving more and more of those ions in solution, right, and so again, that's why we need to consider these kind of effective concentrations, the activities of ions in solution, particularly because of these coulombic interactions and such that go on. Okay, so we're going to consider some general salt, right, with a cation M and an anion X. Okay, M, right, is usually a metal, anions often like halides or things like that, right? So that's why the M and X symbols, right? Where the metal has some charge Q and the anion, right, X has some charge P. Okay, and so when this breaks apart, right, you get P, M, Q plus, and Q, X, P minus, right? Okay, right? And some ideal mixture of these things, right, you just have P times the chemical potential of the cation plus Q times the chemical potential of the anion, right? For a real solution, you have that same type of thing plus the corrections to those chemical potentials based off of the activity coefficient, right? Right, if you recall, when you're talking about activities, right, you can rewrite this chemical potential stuff in terms of the idealized values of the chemical potential plus some correction, some real-term correction. That real-term correction ended up being R times T times the natural log of that activity coefficient. Okay. Right, and so I'm going to combine these two terms, these natural log terms, right, to get RT. I put P in the exponent here and Q in the exponent here, so I can add these two terms together to get RT times ln of gamma plus, right, the cation activity coefficient to the P power, the anion activity coefficient to the Q power. Got the minus here, right, because that's gamma minus, right? And what I'm going to do is I'm going to define what's called a mean activity coefficient, which is just the P plus Q root of that product of the activity coefficient of the anion times the activity coefficient of the cation. Okay, and I'm going to use that activity coefficient, that average, right, mean activity coefficient, that average activity coefficient for both the cation and the anion in my solution. Okay, right, so that the chemical potential of the cation and anion, their deviation from ideal values are going to be the same. Okay, because again, that deviation comes from what is that activity coefficient. We're just basically going to assume that they are the same, right? And so, right, this then generalizes and kind of spreads out this non-ideal behavior equally amongst the cation and anion solution. Okay, well, that might not be 100% correct. It's a very reasonable approximation to do this, and so that's what is done. Okay, so again, I'm going to use this mean activity coefficient, gamma plus or minus, which is the average activity coefficient of the cation with the anion. Okay, and we use that then for the activity coefficient for each of the two ions in solution. Questions so far? All right, so what is that mean activity coefficient? Well, we can get it from the Debye-Hückel limiting law, which says that the log of the mean activity coefficient here, gamma plus minus, okay, is equal to minus the absolute value of the charges of the cation times the anion times this coefficient A times I to the 1/2. We'll talk about what I is next slide. A here is just a constant, which is equal to a bunch of other constants, right? All these wonderful constants that you do not need to memorize, know, or remember whatsoever at all, ever. I have no idea. I can't remember all this stuff, right? F cubed over 4 pi NA ln 10 P B naught to the 1/2 power divided by 2 epsilon cubed R cubed T cubed, right? Like, screw all that crap, right? A lot of constants thrown in here. Doesn't matter. Basically, in water at 25 degrees Celsius, that big old constant just comes out to be 0.509. Okay, and that will be given. You don't have to memorize that, but that will be given, right? And in this class, right, we're just dealing with water solutions where that constant is going to be 0.509. So if you want to memorize that for this class, you're welcome to, but you don't have to. You will be given it. Okay, right. So A is just some constant, right, for water. At 25 degrees Celsius, that constant ends up being, again, 0.509. I here is a dimensionless number, and it is called the ionic strength, okay? And it is related to roughly the average charge in this solution, right? So you have 1/2 times the sum of the charges of your ions squared times their concentrations, right? B naught here is just 1 molal. So this is just there to make sure this is a unitless quantity, okay? So I, again, is a unitless quantity, and it gets that way because we divide by 1 molal for all of our concentrations, right? And so again, right? And so again, this is sum of your charges squared times their concentrations, which again is giving you roughly an effective like charge in the solution, okay? Right? And that's why it's related with sort of the ionic strength of the solution, right? How strong of an ionic presence do you have in your solution, right? How much ions do you have in solution, okay? For say 2 ions, right, the ionic strength, right, would just be 1/2 times the concentration of the cation times its charge squared plus concentration of the anion times its charge squared, right, divided by 1 molal, again, just to get rid of the units. Okay. Now note, okay, I'll note this here, and we'll see this in an example later in class. Okay, the ionic strength for a solution is something that is a quantity of a thing of the total solution. Okay, of all ions. So you can have multiple cations, multiple anions in solution, right? And the ionic strength is a sum of all of those things together. Okay, but that mean activity coefficient, gamma plus or minus, is unique to a specific cation-anion pair, right? And specifically, you're talking about the cation anions that like came from the same salt, right? So if I have multiple cations and multiple anions in solution, right, I have a mean activity coefficient for each cation-anion pair in solution, right? Not each possible pair, right, but each pair in terms of like how they were dissolved in solution, right? So that aluminum chloride, that example we did at the beginning of class, right, that would have its own mean activity coefficient. If I put in sodium chloride as well into that solution, that would have its own mean activity coefficient, and so on and so forth, right? The mean activity coefficients, the number of mean activity coefficients is equal to the number of salts you've dissolved in your solution, okay? While the ionic strength is just one. Each solution has an ionic strength no matter how many different salts you add to that solution, okay? Right, this is the sum of all ions in solution. Okay? And this is important because this is related to why in reality, right, you can have the solubility of a salt decrease in a solution without any sort of common ion effect, right? If you remember, right, from general chemistry, and you talked about solubilities of some insoluble salts or things like that, right? Let's say silver chloride is an insoluble salt. I believe it is, right? Right, if you added chloride to the solution, you reduce the solubility of silver chloride, right? Well, I could reduce the solubility of silver chloride by adding sodium, sodium iodide to solution instead of silver chloride. So there's no common ion effects, nothing going on, but purely the fact that if I add a bunch more ions to my solution, it makes it that much more difficult for silver and chloride ions to dissolve and form in that solution. Okay, so the solubility of a salt, right, will actually depend on if there are other ions already in that solution, and you can reduce the solubility of a salt by just adding more ions into that solution, and that's related with effectively increasing sort of the ionic strength of that solution. Okay. Questions? All right. Right. So this table here is just sort of right. The sum if you have just a cation and an anion solution, right, and the fact that that cation's concentration molality came from the total molality of the salt, and the anion came from the molality of the salt as well, right? And plugging in charges, right? Depending on the charges of your cations or anions, you can calculate out what kind of this K here is, which is 1/2, times some stuff or whatever. Right? And you can work out and see kind of where these numbers come from, but I don't know. So there's this table here that's presented in the book. I just kind of throw it up here. Personally, I just work this out each time instead of trying to like memorize, oh, I have a +3 -4 salt. That means it's 42 times the salt's concentration, right? I'd rather not try to memorize this table. Instead, I'd just rather calculate it myself by knowing this formula. But I present it just in case for those who are interested.
Did you say B naught was always gonna be 1 mile?
Yeah, B naught is 1 mol. It's right. We use it when we do, just like P naught is like 1 bar. We're talking about like pressures of gases and things like that, and we get to equilibrium later. Right, B naught is 1 molal. It's just there to basically get rid of your units. It's right. Often you'll see me write this ionic strength without dividing by B naught, because I just intuitively just like ignore the units when talking about the ionic strength, because I know I'm dividing out everything by 1 molal to make sure it's unitless. But yeah. All right. So I have the complete dissociation of a 1,3 electrolyte, okay, something like aluminum chloride here, in an aqueous solution at normal concentration of 0.1 molar or 0.1 molal. The ionic strength will be what for this solution? All right. Anyone have any thoughts?
It's on there, yes, I know it's on there, but I don't. I know it's not on.
All right. Right. So if I have, say, aluminum chloride, right? Thank you. Right, with 0.1 molal, right? So I here is 1/2 times the charge of aluminum squared plus the molality of aluminum, right? Plus the charge of chloride times the molality of chloride, right? That's what the ionic strength is, okay? Right, for chloride, the charge is 1. Oh, that should be squared, right? For aluminum, charge is 3. Okay, so it's 3 squared, 1 squared. Yeah. Right. Yeah, I mean, charge is -1 technically, but yeah. Right, then the concentration of aluminum is still that just 0.1 molal. Okay. And then for chloride, right, it's going to be 3 times that concentration, so 3 times 0.1, right? And so I get 9 times 0.1 plus 3 times 0.1. All of this multiplied by 1/2. So that's 12 divided by 2 is 6 times 0.1, which equals 0.6, is the ionic strength of this solution.
In that problem where it says the aqueous solution is at a nominal concentration of 0.1 molal, does that mean, like, I would assume that that means the entire solution totals to a concentration of that. So I thought like the molal of aluminum would be like 0.025 and chloride would be like 0.075.
Oh, no, it just meant like, let me go back to,
Like you dissolve 0.1 moles of aluminum chloride.
yeah. Yeah, so it's saying like a nominal concentration, it's saying like the effective like total concentration is like 0.1 molal, right? Saying nominal concentration is sort of saying like ideally it has a concentration of 0.1 molal. Now it actually might not be 0.1 molal fully dissolved in solution, right? It might have some solid hanging around and things like that, right? But ideally the concentration is 0.1 molal is kind of what that was supposed to kind of mean there.
Okay, so yeah, assume that it's 0.1 molal of the aluminum trichloride, and then it dissociates to the values that you're talking about?
Yep.
Or, okay, okay.
Any other questions? All right. So the mean activity coefficient of a 0.005 molal potassium chloride solution is 0.92. What is the reaction quotient Q for this solution? All right. Anyone have guess or thoughts? More than a guess? What is Q? What is the reaction quotient? Will not remember. Gen Chem.
I don't remember how to calculate it. I know it gives you like an estimate of if
What
like the
what
reaction
is
will
the
suit a
equilibrium
product.
constant expression?
Concentration of products over reactants.
Yep. Right. So KCl, right? That breaks apart into K plus Cl minus, right? Solid, aqueous, right? K here is just concentration of K plus and concentration Cl minus, right? Which is the exact same expression for Q. It's just I'm not necessarily, sorry, K plus Cl minus, right? I'm just not necessarily using equals K plus times Cl minus, right? For Q, you don't use the equilibrium concentration. You just use whatever concentration you want, right? But the exact same expression is the equilibrium constant K, right? And so calculate Q, I just need to do this, which with we're using activities is the mean activity coefficient times the molality times the mean activity coefficient times the molality, right? Since this is a 1-1 charge system, right? The molalities of potassium chloride are the same. This is equal to the concentrate, the molality of potassium chloride salt. Okay. And right, and then we're given the mean activity coefficient gamma, which is the same for the two things. So it's just going to be gamma times B squared. Okay. Which is going to be 2.1 times 10 minus 5. Okay. All right, so it's going to be 0.92 times 0.005 squared, which is B. Or at least hopefully should be. Huh? Okay. All right. Questions? All right. So given the equations above, right, calculate the mean activity coefficient gamma plus or minus of 0.005 molar potassium chloride solution at 25 degrees Celsius, given A is 0.509. Okay. Right, it's not necessarily going to be anyway, but yeah, so calculate mean activity coefficient given this information. All right. So if we were to calculate this, right, first we calculate I, the ionic strength, is 1/2 times the charge of the cation squared times its concentration, plus the charge of the anion squared times its concentration, which just gives you, right, 1 times the concentration of potassium chloride, which was 0.005. So the ionic strength, right, is 0.005. So then plug that into the equation here for the log, gamma plus or minus. That's minus 1 times 1, right, which gives us 1 times 0.509 times the square root of 0.005, gives us negative 0.036. And then you just take 10 to that number to get gamma plus or minus, right, to get rid of the log. And so gamma plus or minus is 0.92, which is, right, what was given in the previous problem. Questions about how to do this calculation? You have to do it often for these type of problems, so. All right. Okay, so the Debye-Hückel limiting law does do a decent job of giving us what the effective concentrations are of ions in solution. Okay, but it's not perfect. Okay, it works really well for low ionic strength. Okay, especially and it especially works well for ions that have low charges, like sodium chloride, right? A 1,1 charge system, 1,2, or magnesium chloride, right? As you get the higher and higher charges on your ions, 2,2 or a 3,3, you know, pair for salt, right? You start getting to the point where it really breaks down the Debye-Hückel limiting law. So the Debye-Hückel limiting law is the straight dotted line on this plot, okay? And then the solid lines are the actual data for the log of the mean activity coefficient with respect to the ionic strength, right? The ionic strength is calculated using what the ideal concentrations would be of the ions in solution, right? And then the mean activity coefficient is measured by measuring the activities of the ions in solution by measuring their actual concentrations, right? And so that's how experimentally you get this, okay? And you can measure the actual concentrations through a number of different means, right? Depending on the salt and things like that. But yeah, and so, right, you see here, again, as you get higher and higher ionic strength, right? So the x-axis is the ionic strength to the square root power. It's multiplied by 100 so that, you know, the numbers here are like 0.004, 0.008, 0.012, right? Said 4, 8, 12, 16, right? So, but again, as you see, you get the higher and higher ionic strength, our deviation starts going away. And so if you want, one wants to try to be more general, you can use the extended Debye-Hückel law, okay, which is just this limiting Debye-Hückel equation here with these correction terms, 1 plus b I to the 1/2 plus c I, okay, where b and c are just dimensionless quantities that are determined experimentally, okay, right, and so here the limiting law is again this dashed line, extended law is the solid line, and the circled dots are the experimental data, right? And so it still does very well. Now, when you start getting to very, very high concentrations, even this extended Debye-Hückel law breaks down, okay? But this at least shows you, for example, how the, right, this activity coefficient, right, depends on the ionic strength, right? And this kind of formulation here. Okay. In general, in this class, we'll mainly just use the, you know, the Debye-Hückel limiting law to calculate these guys, right? But in the lab, if you wanted to be even more precise, you could try using something like this, okay, with fitting these B and C values and such. Huh? I don't know. I forget what salt is here. So I know the color is the same as like the magnesium sulfate. But I'm not so sure if it's magnesium sulfate. I don't know. Sorry, I forgot. Yeah, no, that's a good question. I forgot. I mean, so this plot, like this plot, are both taken out from the book. So you know, look in the book. Most of the plots I get are from the book. All right, so let's do some questions. Okay, so that's it kind of for the new material, right? So again, the sum up of kind of the material that we're presenting today and going over and doing examples with, right, is the idea that ions in solution, right, have reduced concentrations from the ideal values, right? We can get those through the activities. To get the activities, we got to calculate the activity coefficients. For ions, we use this mean activity coefficient, right, the average activity coefficient for the cation and anion, right? This is related with the charges of these things, the concentrations, and the ionic strength of the solution. Okay. Right. And and so yeah. And so we'll do a lot of this, and then we'll revisit this stuff when we talk about electrochemistry, right? Because electrochemistry, you got plenty of ions floating around the solution, and we'll use this to then talk about right, how to calculate actual cell potentials, not necessarily the idealized values within activities and such. So, add equations to that slide. Okay. Right. So here we want to know what is the mean activity coefficient and activity of a solution of 0.01 molal calcium chloride and 0.03 molal sodium chloride. Right. And really, I should be saying, yeah, mean activity coefficient and activity for each ion in solution. Okay. So what is the activity coefficient? Mean activity coefficient and activities for each of these ions in solution. Right. So, if and just as a note for those who are interested, right? I believe I will double check this after today, but I'm pretty sure that again the equations I give are equations that are given based off of ACS final, even though we're not taking the ACS final, just being consistent throughout semesters and things like that, right? And so this equation here, the Debye-Hückel limiting law, is something that's given, but this equation is not. The ionic strength is not given. That ionic strength equation is not given, but this equation, calculate gamma plus or minus the mean activity coefficient, is given. Okay. And I find it strange that they give half of sort of the relevant equations here, but that is what it is. So this first equation is given, second equation is not. Okay. All right. So I have a solution of these two salts combined. Okay. We want to get the activities and mean activity coefficients, these ions, right? First thing we need to get is the ionic strength of the solution, which again is total for the entire solution, 1/2 times the charge. Right now, calcium chloride breaks into Ca2 plus 2Cl minus, right? And NaF breaks into Na plus F minus, right? Huh? Oh my gosh, sorry, I forgot I froze. Thank you so much. All right. Right. A plus minus, right? And so, right, if I want to look at this ionic strength, right, let's just start adding in, right, the charges of my ion. So calcium, so I'll do calcium first, right, which is a charge of 2 squared times its molality, which is 0.01, plus say the chloride, right, which has a charge of 1 squared times its molality, which is going to be 2 times 0.01, plus then sodium and fluoride both have a charge of 1 and a molality of 0.03, right? So 1 squared times 0.03 plus 1 squared times 0.03. Okay. So what is this? I 1/2 4 plus 2 plus 3 times 0.01. The 6, 10, 12. So, 0.06. Okay. So that's the ionic strength, if I did that math correctly in my head. Okay. Yeah. Right. And so then, right. And so again, the ionic strength is the same for everything in solution, right? It is a solution quantity, if you will, right? But then the mean activity coefficient is for a given salt, right? So the mean activity coefficient for, say, calcium chloride, right, is equal to 10 to the minus, right? Charge of calcium is 2, charge of chloride is 1, times 0.509, times the ionic strength, 0.06, to 1/2 power, right? Right, the log of this equals minus those charges, absolute value, right, times that A times I to the 1/2, okay? And then the gamma plus or minus, right, for sodium fluoride is 10 to the minus 1 times 1 times 0.509 times 0.06 to 1/2, right? So the main difference between the mean activity coefficients of different salts is whether or not the charges of those salts are different, right? If they're all 1-to-1 electrolytes, then they all have the same mean activity coefficients, right? If they're all 1-to-2 electrolytes, they all have the same, right? But since, right, sodium fluoride is a 1-to-1 electrolyte, calcium chloride is a 1-to-2 electrolyte, right? Or salt, or whatever you want to call it, right? It has a difference because the difference in charges of the anions and cations. Okay. But otherwise, they would end up being identical. Okay. Right. And so then say that the activity of calcium, right, is then just going to be the mean activity coefficient, calcium chloride, times the 0.01 molal of calcium, right? The activity of chloride, right, is the mean activity coefficient of calcium chloride, right, times 0.02, okay? Because again, right, I get 2 chlorides, right, from the calcium chloride, so it's the concentration 0.02, right, so on and so forth, right? So flipping back to the slides here, right? So those mean activity coefficients come out to be 0.56 and 0.75, given what we have here, right? Which then tells us the activity, right, of, say, calcium is 0.0056, right? So half the actual, the theoretical concentration, right? Chloride activity right? 0.012. And then for sodium and fluoride, it's 0.022 and 0.0225, right? For both of those. Okay. And so in this example, in the solution, right, the activities are significantly different than their actual ion concentrations, right? 25% different, almost 50% different for these things. Okay. Any questions about this? About these examples? Okay. Right, so we can do a lot of things with this stuff, right? You know, we could then say, right, let's say one of these salts is insoluble, and we can ask, like, is you know, is some amount of solid able to precipitate, things like that, calculate equilibrium constants and things of that nature. Okay. We'll talk more about some of that stuff as well when we talk about equilibrium next time, right? Or not next time, but on Friday. Okay. Right, but you know, but let's say I'm dealing with some sort of insoluble salts, right? The fact that the activities of these ions is, say, for calcium, like 50% less than the theoretical concentration, right, makes a big difference in the overall solubility and things of that nature, right? And so, yeah. Any questions about this example? How we did it? Why we did it? So that is it for today. So like I said, for those who are here in class, I'll hand out the exams. You can pick them up. I'll post solutions to the exams online today for those who would like to look over them. Okay. And if you aren't here today and would like to pick up your exam if you took it in class, I'll try to remember to bring it Wednesday, but otherwise, you can always come with me to my office or stop by my office to pick it up. Okay. So any questions from those here on Zoom before I close out the session?
I was just going to ask, on Canvas, the homework for number 5, it shows it's blank. I didn't know if that was a mistake or if you just hadn't uploaded it yet.
Probably I forgot to link the file there. I think the file is uploaded if you go to the files, but I probably just in the homework I forgot to link it. So I'll change that to link the actual homework file in the assignment. I think that's probably what's going on there. So I forgot to link that. But if you go to the files tab on Canvas, you should see it there.
Okay. Yeah, I see it now.
Okay.
Right, thank you.
No problem. All right. See you guys on Wednesday.